Welcome, everyone, to the Convo AI World Podcast, where we interview builders, developers, and the teams that are really forging ahead the solutions and the conversational and voice AI world forward. And today, I'm so lucky to be joined by Andrew Seagraves, VP of Research at Deepgram. Thank you so much for joining me today.
Thank you for having me. I'm also extremely excited to be here. Great to be chatting with you.
The other day when we met, it was like we had a really great conversation. So I've been looking forward to this all week, basically. For anyone that's not aware, Deepgram is one of the leaders in speech-to-text recognition, and most likely you are using them and might not even know it. So welcome, and let's kind of get into it.
Okay, sounds good.
So what motivated Deepgram to build a speech-to-text engine kind of from the ground up using that end-to-end deep learning?
Well, that's a great question. That takes us back to the early days of the company when it was founded, and they chose to focus on that early on. That is not actually the first problem that they tackled. So the founders were originally dark matter physicists, and they were doing a lot with audio. They were using audio signals and like shooting them into the earth and then measuring what came back and then trying to use machine learning to understand whether or not there was like dark matter present. And so they had some very strong expertise that they were building, but applying deep learning in their particular application. This is back in like 2015 timeframe. They were also doing weird stuff like recording themselves for weeks, like all of their audio, wherever they were, they attached mics to their clothing and they were recording themselves. And so they amassed this very large volume of audio from recording their everyday lives. And they were like looking at their machine learning stuff that they were doing, looking at this large corpus that they would never be able to listen to like find the interesting tidbits. And they decided to try and tackle the problem of like using the machine learning to search the audio just as a side project. And that was how Deepgram started. They went and founded a company. They built a deep search algorithm. In doing so, they actually indexed all of YouTube at the time. And you could like find random audio clips in like a YouTube scale corpus. They demoed on stage at GTC with Jensen. This is like very early days. But they realized at that time that like search was not a hot thing and there wasn't like a big market for it. So speech recognition at that time was an emerging green field and there were very few players and all the models were terrible. And so they had this strong conviction from the beginning that if you combined a system that's learned end to end, a single network, and lots of high quality data, that you could build a model that could transcribe sort of like potentially any human in any situation. It was just one of the early convictions that they had. They went about like building an early prototypes, like 2016 timeframe.
That's super interesting. Gotta love that gap in the market, right? Like everything else is terrible, and you're like, actually, I think if we do this, it could solve this solution, right?
Yep. They also kind of got lucky in that there were some early AI adopters from call centers, basically like AI platforms that had many call centers as customers. There's like huge volumes of call center audio that they wanted to transcribe and do analytics on. And that particular domain like is narrow enough that the very early deep learning models that we had actually worked. And you could
Okay.
train on these narrow domains and produce models that were like 80, 90% accurate if you just specialize the data. And that was like some of the early magic of Deepgram models, that they worked for particular applications where there was an interest and a lot of data and people who were like willing to try to use the models. So that was one of the reasons that we have built for scale early on too.
That's super interesting. It was kind of like the approach kind of led them down the path, right? Like, hey, we're here, we have this stuff, we can apply it here. And now, because call centers, like you said, also have that very rigid, structured type data, they could apply it there and kind of scale. That's super cool. What are the most common misconceptions people might have about speech recognition?
I would say the biggest one is that it is a solved problem. I think even Jensen has said that in like his most recent GTC keynote. He said speech recognition is a solved problem. And I think that it is definitely not a solved problem. It's only solved in some very narrow situations. So like it works well in situations where we have a ton of data. So there's particular use cases like call center audio, for example, in English. We have a lot of data. We can train models at scale. And this paradigm of like, large expressive deep learning model trained on lots of data, it works well. And then we've over time collected enough data across a lot of niche domains, or what would have been considered more niche domains a few years ago, in English. And so the models have gotten really strong in English. But I think that like in non-English languages, the models are in general still pretty terrible across the board. And it's just because of the lack of data. And then I would say, beyond just like having data to cover the very broad range of speakers and acoustic conditions that you're trying to model, the other big challenge that is not solved is being able to recognize rare and localized words, like words that are specific, say, to a particular customer or a particular person, like how their name is spelled, for example. Words will continue to be a challenge moving forward, like getting the words right. It's like one of the core challenges that's sort of underappreciated, I would say, in speech to text.
I feel like it leaves a lot of room to grow, right? Like there's still very early days on this sort of thing. That challenge is kind of what you guys have solved on the English side of it, and I'm sure you're going after international and like colloquial, like localized dialects and stuff like that. In terms of how you take the approach for speech to text, really, how does Deepgram like balance this real time latency with the accuracy of the transcription?
That's a great question. So so there's two major use cases for speech to text, and in your question, you're sort of honing in on real time. So where you want the model to be actually transcribing the words as soon as possible after they're uttered by the person, and that is just a very hard challenge. The other major use case is batch or asynchronous transcription, and that's where you have like your 10,000 calls for the day that were recorded at your call center, and you want to be able to transcribe all of them in it's like 30 minutes or an hour or more, like as quickly as possible, so that you can get the insights about what happened today. And so I would say, like, Deepgram, for both of those kinds of problems, we have always worked in a constrained design space where we are trying to achieve the maximum accuracy, subject to like it must be fast and scalable, some like very concrete performance or engineering requirements. And when you operate in this constrained design space, like there are many approaches that do not work well, that otherwise look great, like in papers. Models that don't scale, also like very, very large models, become impractical if you're trying to hit a latency. And so it's pretty simple: small models, constrained design space, and then actually like imposing those requirements from the beginning so that you design with scale and speed in mind.
So really having that kind of from the start, not taking things that will, yeah, they work in batch because batch doesn't matter timing and
I would say, so I'll say like one more, go like one level deeper there, double click, if you will. The data actually impacts being able to solve that problem. So the more high quality data that you have, and the like more localized it is for whatever particular domain you're trying to model, the smaller you can make the model for a given level of accuracy. And so there's like a joint dependence there, if you want to think about it. The better the data you have, the more efficient model you can use. And so we can leverage our data advantages that we have, because we have collected and labeled like a lot of high quality data to actually make the model smaller.
so I love that we're talking about data because data is really at the core of deep learning and that and high quality data is kind of like the grail of deep learning. And like you said, the better the quality of the data, the smaller the model, the more accurate it can be. So can you walk us through a little bit of that model training process, like the data source as pre-processing, that sort of like architecture?
Yeah, I'll start with like a big picture. How do you train like a state of the art speech recognition model today? I think like the simplest way to do it is that it's a two-stage process, and this is typical across many deep learning models. You have like a pre-training stage and a post-training stage. And so there's parallels to this in LLM training, the way the LLMs are produced. Kind of the same thing in speech recognition. So in the first stage, you're trying to train with a very large scale of data, as much data as you can get your hands on, covering as many voices as you can get, as many acoustic conditions as you can get, and then as many examples of words being spoken. So this is something that is maybe like underappreciated, that we want the model to have a very broad exposure to speakers and audio conditions, But when you do that, you also increase the frequency of particular words relative to others. So there's this interesting like scale effect that when you scale up the data, like the frequency of stop words, like the most frequent, like ands and does, it explodes. And then you have an emergence of a very long tail of rare words that appear. So basically, the best you can do is just keep scaling the data as much as possible in the first stage, and you train a model on that. So in that case, you're training primarily on data that's crawled from the web, and then you're filtering that data to the best of your ability to isolate audio that has human transcripts, where the human transcripts are good, basically. So that's the name of the game for the first stage, and you get a model that is like pretty good, I would say, and that is how, for example, like Whisper was produced.
Okay.
Whisper is like the first stage of a production grade speech to text training. In the second stage, you specialize the model in post training, and you train it on a much smaller, more narrowly distributed corpus that covers just the domains that you care about. Yeah, you focus the training, and in that case, the data is like very high quality. It must be like basically gold ground truth, labeled by humans that are following a very prescriptive style guide, so that the labels are sort of consistent. In the first stage, you have labels that have been generated by like millions of different humans with no consistency in style, and so then you have to like unlearn that in the second stage, and the model's output becomes
Everything I taught you.
yeah, yeah, and so that's basically how it goes. The magic really happens in the second stage, although the first stage is also important. So one thing I'll say, so it's like something we've observed that we haven't like published, I would say, is that as you scale the corpus in the first stage, there will be a set of words that you've seen, let's say like 10,000 times or 100,000 times. And those words, like you sort of saturate the model's ability to predict those words. In that, if you were to show the model more examples of those words, it wouldn't
It wouldn't help.
it wouldn't help. And then you have this long tail of words that you've seen less than that threshold, let's say 10,000 to 100,000 times. Word error rate depends just directly on how many times you have seen those words. Yep.
It's pretty crazy. So like Whisper, essentially, the thing that everyone claims to kind of be building off of is just like part one of the puzzle. So if you're not applying part two, you're not going to get the right performance that you should be getting out of this.
Yep, that's right. And you get all kinds of what we call model pathologies that result from part one. The model will insert words that aren't there. The model will omit words that are actually present in the audio, what we call shyness.
Seen this, and I've had people tell me, no, that doesn't happen. It never happens. And it's like, but
It totally happens.
it totally happens. And you get like one thing in the audio and then one thing in the transcript, and you're like, they don't match.
Yeah. And it's like customers react to those two failure modes differently. When the model's inserting words that are not there, it can be very creative. And so you like sort of never know what it's going to say. And
Boy.
so that
Oh
makes for a
boy.
lot of interesting failure modes, depending on what the model is choosing to say. But then the silence is just like universally despised by all customers. The model should produce something when words are happening. And that's a big one. Yeah.
That's super interesting to hear. I feel like sometimes missing a word is also a little bit more forgiving because you're like, all right, it just kind of missed the word. It didn't like add to like it's a lot more jarring when there's words added to it.
Yeah, that is more jarring, especially if you're seeing it in real time. It is kind of interesting that like real time speech recognition is just more challenging than batch because you're operating on like small chunks of audio at a time in principle when you really shrink down the buffer of audio that you're sending. And so that's just harder. You have less context. You don't get to see what is coming in the future. In batch, you could see the whole file at once in theory.
Are you constantly like building that? Like as it goes, you're like building on the previous buffer that you got.
Yeah, and there's a tremendous range of different things you can do there from a modeling perspective. But largely speaking, you're like maintaining some state about what you've seen so far and updating it as new audio comes in. And then the model may be doing something like deciding whether or not it's going to emit a prediction at this frame or not. And so real time opens up all kinds of interesting mechanics. But model pathologies are also more prevalent. And then also like real time is the setting where people are watching the transcription live and they see them. So Yeah, for all these reasons, real time is like way harder.
You don't have to tell us. We've been in that
You're well
space.
aware.
Yeah, we're well aware. And it's not just like talking to an LLM, talking to a person and real time voice and video streaming. That's like another one of those things where if someone's talking, you expect it to happen. I think that's like one of those like fine tuning grain things in our human mythology of like we're expecting this to go along with that.
That's right.
So really the biggest challenge in scaling, it sounds like, is not only the part one of the accuracy of the data, but like not oversaturating, like you said. Certain words are just so prevalent that it probably like the more you throw at it, the worse it probably gets, right? Like it doesn't help the situation.
That's right. The larger, like the more you scale the data, there's this like everything in nature, all the like underlying physics of audio, like human speech, if you want to think of it in terms of like the basic physics, like it's all governed by power laws. It's all power law phenomenon. And so like the words that people utter is described by a power law. And like if I had the ability, I would like bring up a plot that you could see right now, or like go to Wikipedia and look at Zip's. It's called Zip's law.
We'll edit it in. So like what should we put in? What's the graphic we should show right here?
It's a graphic that so if you take a very very large corpus of text, and let's say it's spoken text, so
Mhm.
from human speech, and then you count up how many times each word appears, and then you sort it on the x-axis. So you have the most frequent words on the left and the least frequent words, the long tail on the right. You get this curve that is described by a power law relationship between the rank of the word and the frequency. So if you plot it in terms of frequency on the y-axis, and for human speech, that the slope of that is like 2 or something.
So it's relatively like straight. It's not like weirdly asymptotic or anything like
If you plot it in log space, it is.
that.
The thing is that as you increase the size of this corpus, the most frequent words just continue to appear ridiculous numbers of times, and the least frequent words are appearing once. As you go to like the scale of data that we actually are training on, the most frequent words are happening like 7 orders of magnitude more frequently than the least frequent. So you have a huge class imbalance in the data in the parlance of machine learning. You're basically trying to learn these are the classes. You have 50,000 or 100,000 classes that you're trying to learn. It's these words, and you have a huge imbalance in them.
But let's say you guys have solved this, or not really solved it, but you've gotten it to a point where it's good. And we're getting to a point where in real time, like we said, it's tough because you're constantly checking the buffers and updating and deciding. So what are the technical trade-offs between this like real-time accuracy and maybe like compute efficiency? Because if you lock up the machine, it's not going to do anything, right? So how do you keep from overloading it while keeping it?
Yeah. I think there's 2 ways to answer that question. So there's several different like cost, speed, and accuracy trade-offs. And I would say the biggest one for real time, the hardest one to design for, is like how much forward context you accumulate before you allow the model to make a prediction. And so that we think of as, you could think of it as a buffer, or you could think of it as a future context. That's another way of thinking about it. So you could have no future context. As soon as you get an audio frame, you emit a prediction, right? If you're doing that, then you're very likely to be capturing someone who's mid-word. They're in the middle of speaking a word. You actually don't know what that word is yet in a lot of circumstances. And so the model is likely to get it wrong if you emit a prediction immediately. If you allow the model to wait and buffer up some audio and then emit a prediction for that previous frame that you already had, it's much more likely to be accurate. So you have this waiting, how much you're willing to wait versus accuracy trade-off, and the how much you're willing to wait just like determines the latency.
So that's like the queue essentially.
Yep.
I remember like in AR and VR, you have like the, the buffer queue for the video frame, right? And then you can render onto it and then present it to the user. And it's got to be quick before the user like realizes there's a crazy disparity between what they're seeing on the screen and reality, right? And I think it's the same in the speech buffer. You're building this up and then slicing the front. You're like, okay, it's accurate enough. Slice it. Give them the frame. Give them the frame. Give them the frame. Kind of like, and constantly doing that battle, right, where the queue is growing and cutting.
Yes. That was a very good usage of the slicing hand motion there. Very nice visual. That's exactly right. And so if you wait, a half second, then there's going to be a half-second delay between what the person hears and what they see.
But in half a second, that's a lot of data.
That is. No, the models do great. If you give them a half second, yeah, you barely even notice it. But if you shrink it down to like 200 milliseconds, then you start to notice it. And then if you go to 100, 50 at 100 millisecond, there's really like real limits there where you must wait a little bit.
There's only so thin you can cut that, make that buffer before it just becomes like not good anymore.
Agreed, unless you solve the problem of like predicting what that person is going to say, you know, which it does feel like we're maybe heading in that direction.
Who knows? I mean,
What's in their brain.
if you look at what happened with like Genie, right? In the video prediction, the user makes a right turn, the user makes a left turn, the user looks up, the user looks down, it's there. So it kind of almost has to like forward predict that sort of thing. And I wouldn't be surprised if that comes to voice and to everything, that concept of like, okay, have just this little bit based on all this other knowledge. Can we throw something else in there to see if it works or not? But I feel like that would introduce new trade-offs in the latency, right? Because you're trying to like, I know AI and the layers are very fast in their response because of the weights systems, but you're still like trying things at that point to get the weights all right before it'll respond. So I feel like that's like a whole different battle.
I agree. It seems like there's this emerging new field of like real-time AI where you want to be doing these fancy things like you're talking about, like predicting multiple potential realizations of what the person might be about to say, and then like ranking them and picking what you think is the best one, that kind of thing. And that introduces just like fundamentally new model mechanics where you have separate models working asynchronously and then sort of checking in with each other here and there. Like it's probably described by some other kind of like computer science operations. Like it's more like distributed
Yeah,
system.
it's like distributed systems that have some sort of like load balancer, right? Like they're all checking back, and this is the one system that's the source of truth, while everything else just focuses on its own task.
Yep. And maybe there's a way like transformers, you can like sort of view them as like nodes communicating with each other. And there's some really cool, like Andre Karpathy has some really cool description, like paints a beautiful picture of them in that way. And maybe there's like generalizations of that idea of models that operate on graphs, that allow communication across these different streams. And the whole thing could be trainable.
Kind of getting back on topic though, because I know that's like future thinking. We're not quite there yet.
This is sort of like almost the nature of like every research meeting that we have is that we started with some topic and some question, and then we totally have forgotten what that is. And then we've gone 15 minutes over by the end. Yeah.
All right, that means that it was a good conversation.
Mhm.
But let's get back to Deepgram and your approach. So your approach to deep learning really differs from competitors, right? Like most of them aren't doing what you're doing. And how does it differ?
I know concretely like a few ways in which it is different. I would say the biggest difference between what we've done and what competitors have done. I mean, there's probably like two things. One is that like we will not use we just won't do giant models unless they're fast enough. And so we've worked in a design space where the models generally have to be small. And then we've really like focused on the data. I think like getting the data right is really like the biggest competitive advantage and secret sauce that Deepgram has. Now, we definitely have made discoveries about interesting architectures that work well in speech. But I would also say that we sort of like rode this wave of the large sequence model, where like most very powerful foundational models across different disciplines, different domains in AI are based on like sequence modeling, and powerful sequence modeling frameworks like transformers. You take a transformer, you train it on a bunch of data, and generally it like trains robustly, and you get a model that's like good at the end of the day. And this paradigm has like been true. It's been applied across all domains at this point, and it has like continued to work. So we definitely were sort of early on that. I would say we had a model that was kind of like Whisper in like 2020, like late 2021, and that was terrifying because it was like an encoder decoder transformer like model that had the ability to sort of like say anything. It would like listen to the way the model works is that like it listens to the audio and then says what it thinks it hears. Like that's sort of one way of thinking about it. Like the encoder gives you some rich representation of the audio. The decoder is basically just like a language model that just predicts, one token at a time. And it kind of looks at the audio and gives you a prediction.
Sounds like you're playing the record backwards.
And anyway, it was scary to put one of those models into production.
Would it just say random words or like how?
Well, like we talked about earlier, like the model sometimes will say things that are not in the audio, like if the training data is noisy and there is in some cases a lack of correspondence between the audio and the transcript that you have, you get more frequent model pathologies. The models have degrees of freedom to do weird stuff, where the previous generations of speech recognition models, which were all encoder based, and they used a mechanism called CTC, like those models are very constrained. Like they don't have the freedom to say whatever they want.
It brought up an interesting topic around like just that the early days of just being early into this space and seeing it how it matured and kind of riding the waves. Like you said, you kind of built on this very stable foundation, which allowed you to do something that was at the time probably revolutionary, and even now like still industry leading. So in this time, what verticals have you guys seen like the most adoption across? Is it call centers, voice assistants, or something that most people?
But yeah, like I would say most verticals are 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 becoming like strong adopters. Essentially anywhere where you have a decent volume of data available, and that's now becoming true. Yeah, audio data, like that's now becoming true across most verticals. It's just that like deep learning models that work reasonably well have been out long enough that people have been willing to use them now. And that leads to like vehicles to collect data and label it, over a certain period of time. And so, if you name the top 5 or 10 domains that you could think of, finance, earnings calls, meetings, call center, like anything to do with call centers, food ordering, which was historically a very challenging one, is now like models work really well in these scenarios where the person is like outside or say in the field, and you're transcribe them, even across like a lot of those, it works well. So I would say across most verticals.
That's huge. So it's kind of like everyone needs this. We're seeing just that explosion of how AI is really helping everyone at this point.
Yep. And then it becomes like if the model becomes robust, this is not something you asked, but I'm going to say it anyway. The model becomes robust to that acoustic environment and like is capable of sort of transcribing anyone who speaks in that environment, but like getting the words that are rare and localized to that domain are the thing. So like you could think about medical as a great example of that. Like, and then all of the sub verticals that are inside of medical or subdomains, all the medical specialties where doctors are going to be transcribing, say, their clinical notes and saying all kinds of weird drug names. And the model has to be capable of transcribing all of them. So, like, the model may be really good in terms of the acoustics of transcribing doctors in rooms, because that's like a relatively straightforward, frequent problem. There's only like so many rooms, a range of room sizes out there, doctors' offices, but the words are the thing that's hard.
So it comes right back to that data, right? Like that initial data set, probably the labeling of it, like how clean is that labeling?
Even just knowing what the important words are, I think becomes like a hard frontier problem. Like what are all the medical terms that the model should know for a particular domain or a particular customer? The customer may or may not have a good idea of that, to be honest.
And they might like mispronounce the word and have their own way of pronouncing the word, right? Because everyone kind of does that. You see it in weird, random ways.
That is so true, and it almost makes you laugh because you have use cases where like this is a very common one where a customer is calling in to their pharmacy and like the customer doesn't know how to say the drug name, and the pharmacist doesn't know how to say the drug name, but potentially like no one knows how to say it. So like there's this incredibly broad distribution of possible pronunciations of the word. No one even knows what the correct one is. Like, how do you discover that information?
But as a human, you're able to be like, well, I've seen this word that could kind of look like that thing, right? But as an AI, that's a different story. It's not hallucinating the mispronunciations unless it has that data point to kind of like build upon, right?
Exactly. The models these days. That's a great visual that you just painted there. It's sort of like if they've seen the model in training some number of times, they'll be able to predict that word. They will be able to produce it in its output. But if they've never seen the word before, like they don't know how to spell it. And they might produce some mangled looking acoustically right version of it. And so like just being able to spell is like a crucial capability.
Becoming a spelling bee champion.
Really what the speech recognition models are spelling, you want that they're spelling bee champs, or at least we aim for them to be. Yeah.
Because it's like, give it the word, use it in context, type it out.
That's right. And then LLMs now the LLMs are so magical that the LLMs are really the spelling bee champs. I would say like they know how the word should be spelled in many cases, and they can see the mangled version of it from speech to text, and they go, actually, you probably meant this, and you can edit the transcript and like sort of insert the right word.
Super interesting. It's like it takes that concept of LLMs being autocorrect or autocomplete, on steroids, kind of applies it here too in a way that actually helps the end user and the end experience. Like, it's okay if the TTS kind of mangles certain words that it doesn't know, because hopefully the LLM will be able to kind of reinforce and fix some of those errors.
Yep. And I'll just mention one thing about on that specific topic. It is interesting that that idea is now sort of coming back around again, because that is how we originally, like within Deepgram, started experimenting with transformer architectures. So in 2020, there were a handful of companies out there training, what would now be considered small to medium scale LLMs. 100 million parameters scaling up to a billion parameters. That was like as big as they were back then. And so you had some early models that were open sourced, that were, language models. And we did some early experiments. We were like taking our encoder speech to text model and like bolting the pre-trained LLM on. And then we had this like Frankenstein model that we then tried to train LLMs. And that led to some very interesting findings initially. But the intuition there was that the LLM would be like an error corrector. That was why we first tried that. And it worked okay in that setting when you were sort of explicitly using it for that purpose. But the LLMs were also like too inventive. So they would often make changes that they shouldn't be making. And like there were positive interventions and negative ones, and they kind of cancel each other out. And so anyway, those hybrid like speech to text autocorrector models they never got shipped.
They,
But then
they just didn't make it.
they did lead to then like sort of discoveries about just training a big transformer on a bunch of data, at least within our company.
That's huge. Kind of shifting gears a little bit, we talked a lot about like not just like specialized speech, but earlier you brought up like multilingual, accented speech, that sort of thing, live environments. How are you guys really approaching that sort of thing? Is it we got to collect more data and just like hammer in on the data, or are there other ways that you can supplement?
Yeah, there's other ways. I mean, so that's a really interesting one. Historically, we have collected data. We have our production system, and there's like data streams coming into it. And for Deepgram, for a long time, we've worked on active learning, where we try to identify amongst this very broad, extremely diverse corpus coming into our production system, what are the interesting data streams that we should sort of be sampling from. And right now, a lot of those would be like non-English data streams where we have data scarcity. And now there's a lot of people using models for non-English. And so like you could definitely apply the same approach that we've taken, which is like you label a very small subset of the data that's coming in, the rare, interesting stuff, and you basically use humans to do that, which is slow and expensive. And so there's like different ways that you can use humans. You can use them for different purposes. And so what we're doing now, instead of that, like we are attempting now, given that generative modeling has become more and more powerful, we're attempting to build models that can generate the data that we need. So audio and speech generation models. And this is really an emerging problem that not a lot of people are working on yet, but I would characterize it as learning how to generate complex real world audio. So that's generating both like people speaking, very broad, diverse speaker base, and then also the complex audio conditions that they're in. So
Reducing the noise and
yep, reproducing the noise. or maybe they're on the street talking into their phone and you have traffic noise, you have other people in the background, they're in a crowded cafe. You can imagine like, all kinds of different scenarios. And so this is a frontier problem that we're trying to solve. We think that this is going to be like the fastest path to like massively improve non-English, especially low resource languages where we're just simply not going to have data scale. And it would take way too long to be able to accumulate the scale that we need. We think we can just generate it. And so when you change the paradigm, now it's not like let's just use like humans brute force to label data. It's like let's use humans in other ways. If we have a sort of like a finite human effort budget that we can apply, and it becomes more about like identifying what are the interesting data streams that we're trying to generate, and then helping to build the auxiliary models that are needed to do clustering and embedding and all kinds of things like that in support of synthetic data.
That's huge. So it's kind of like really shifting the approach, but also kind of, I feel like in line with how the industry is shifting its approach in general. Like there's only, you said, finite human resource, but I feel like there's finite human data. And for AI that's constantly hungry for new data, it's something that you have to solve for. Because like what happens when you've scraped all the internet, right? The internet's growing, but not fast enough. The data sets are growing, but nowhere fast enough for this thing.
That's exactly right. And that's like one of the reasons, like you can kind of see this in language modeling, where because we've sort of hit limits on the scaling approach, maybe in terms of the volume of data that you would need to make the next incremental improvement in the model in pre-training, now focus has shifted more towards post-training and using reinforcement learning to teach the model new capabilities in post-training, and then leveraging like test time compute basically. And so like the focus has really shifted. And that's just because like there's not enough naturally occurring data that can be mined to keep making progress in pre-training. And so now that problem has shifted more to like identifying problems where you can use humans or intelligent machines as like verifiers in a reinforcement learning setting. I actually do think that there's going to be a similar paradigm shift probably in audio. And it's not because, well, it will be more or less for the same reason that we're not going to be able to continue to make progress with like very, very large scale pre-training, and simply just because like the audio doesn't exist to be able to do that.
Becomes a new challenge. But shifting away a little bit from challenges and maybe thinking about the customer. You guys work with so many customers and they do so many really cool things. Can you share a story where like Deepgram's tech kind of made a meaningful impact for a customer?
Yeah, totally. So there's a lot of examples that we could point to. I would point to like one category of example of audio conditions, and then maybe I'll talk about like one specific customer. But so we touched on this a little bit earlier. Applications where you're trying to transcribe like a human who is in the field, out there doing their job, or they're in the world, and they're not like in a studio with a podcast mic. And so there's like all kinds of complex information sources around them. And a great example of this is like air traffic control. And a particular example of this would be like, NASA, like recording and trying to transcribe in real time like what the astronauts are saying in their acoustic environment. So a very notable customer that we've had in the last few years is NASA, and we built models specifically for them. And this approach of like taking a general model and training it on a very narrowly distributed data set, even if that data set is complex, it's narrow enough, the model will work really well. And that recipe, applied and worked well. So we have like the NASA model.
It's so cool.
But there's like a huge range of applications where we're going to find similar things. When people are going door to door and they have a mic attached to them, like that, anything like that. Food ordering is another big one.
People love to order food and there's only so many people that can answer the phone, right? And take the ticket. And I feel like there was a boom at one point to like order everything online. And now it's come back to like, actually, I'll just call the place, just pick up the phone. And they're not equipped for that kind of volume to just like pick up the phone and call you the same way they are hitting up.
That's true. That's one where the models are likely to work. They do need some basic capabilities, like they need to be able to differentiate between if somebody says like number one or number two. You know, the item, getting the item right is the critical thing there. That
Oh, yeah,
just
because that'll just completely ruin someone's day.
it does. And up until like last year, like that was a real problem. You know, It's like when you hear from customers in the food ordering vertical or segment, like the models sometimes transcribe number one or sometimes they transcribe number three. And the reason is that like the reason why that might happen, even though those words sound super different, like and they do for sure, is that sometimes the audio is so degraded that what the person is saying is like what we say indiscernible. So there's a ton of food ordering audio where the customer's audio is just indiscernible, and in that case, the model just hallucinates what it thinks it might be. So it's sort of just like randomly picking number one or number three in that case.
It's like the person at the drive-through. Can I take one? Yeah, yeah, I'll take a number one. Number five.
Like that's what it would be. And now, yeah, so now it's sort of like you can imagine of like in a voice agent context, the speech to text is hallucinated, the order number, and the agent says back to a number five. That is like now happening in the voice agent systems. Um, but
Frustrating in a whole new way.
yeah, another one that customers really dislike is if the model like says the wrong, like says an item, a menu item, but like from some other company because it's been trained on like all this different data. And so if it's just sort of guessing at what it's hearing and it hasn't been properly like contextualized and scoped, like this is only, customer A, and it produces a menu item from customer B, that's really bad. Like,
That's super awkward. That's like, did they pay you to say that?
and they do have the freedom to do that.
Yeah, because they're at the end of the day trying to use their judgment, quote unquote, right, based on the weights and things that they've been trained on. So speaking of judgments and weights, what's your view on some of these more like open source alternatives? So we talked about Whisper. I think NVIDIA has like Nemo. How do you guys see
Yeah.
those?
Yeah, so I think that the quality of any open source model or like any speech recognition model is a direct reflection of the data that it was trained on. And it's like an open source model, there are a few data sources in the world where you have scale. And so, there's like, um, for example, podcasts, a lot of podcasts in the world where there are transcripts available, or you could potentially produce transcripts using a different speech recognition model. All right. And so a lot of these open source offerings are trained on particular data distributions, and you might expect them to be good on those distributions and not very robust across the board.
So they don't work in real world environments.
Definitely. Yeah. I mean, like they're going to work, they may or may not work in the data distribution that they were trained on, and they're definitely not going to work in the real world, where the data is like almost certainly outside of that distribution, and there may be like a new way of training speech to text models that emerges where like you take a crappy off the shelf model that is like transcribes okay and you put it into a particular application and like figure out a way to update its weights, based on how it's performing in that application, like the task that it's associated with trying to perform.
So it's almost like tuning the model for what you need to use it.
Yep, tuning the model. I mean, you can imagine like a reinforcement learning kind of approach where you're using this model as part of a pipeline to perform a task. And there are errors in the speech to text model that lead to task failures. And then there are like times when it actually works, assuming it works at least some portion of the time, where you get a task success. And if you could figure out a way to like structure a reward for the model and sort of back prop that through the speech to text model, it is possible that you could conceivably make a model better this way.
It's just easier to use Deepgram.
Why go to all that trouble when there are
Exactly.
things that do actually work? Yeah. Yeah, and I mean the big, I mean a bigger issue besides the model just that doesn't work is that like you have to orchestrate like the real time orchestration like um, uh, is very challenging. Like being able to ingest audio, stream it through the model, produce inference results with very low latency, and return them super fast. That's a whole other problem. It's like equally challenging. So
And that's a little bit more towards the grail of what you want to be focused on, right? Like not laying the foundation of trying.
yeah, exactly. That is what a lot of companies like where they're able to have more impact. It's like figuring out how to deploy the model like close to themselves, so maybe on their own hardware in order to minimize latency for their application. Yep. Get the model as close as they can to where the audio is actually being generated.
Makes sense. It's like the ultimate edge is on device.
That's right. Unfortunately, like a lot of the speech recognition models you can make them small enough and quantize them. You can get them close to being able to run on device.
At least the voice activity portions that can then lead to the larger models that can do the transcription and things like that, right?
Yep, yep, that's right.
In terms of like, my next question was going to be around, do you see this becoming commoditized? But I think what we just talked about is like, no, because they're like, yeah, you can run it on edge, you can run it on device, but there's always so much still to be done in the space, right? Like it's not quite to the point where it's going to be commoditized and consolidated.
Yeah, I agree. I mean, batch, you could argue that like batch transcription starting to approach the point where it becomes commoditized across a lot of use cases, but real time, definitely not. No, that's like a frontier for sure.
So batch is going to become like the staple. Like if you don't offer batch, what are you doing? And then everyone competes on the real time, which would make sense because that's a thing that's constantly changing, constantly needs.
Yep, that's right. And there are hard batch problems that I would say are unsolved. So like it's the statement that batch is going to become commoditized. Like
Well, but general, like the general task. Yeah.
yeah. But there are still hard problems in batch that I would say are unsolved, like modeling multilingual speech and code switched speech. So, like if the person is changing language while they're speaking, that's a hard problem for either real time or batch. That's definitely not solved yet. And then another one is just being able to model the writing systems in all these different languages and have the model produce formatting that is like appropriate for that language. And so the formatting of the output is another like core problem that is not really solved, I would say, across languages yet.
There's just so much to explore there. I mean, we could go into this like whole frontier thinking. I think that's probably like a better place to go than really harping on like product and strategy and landscapes. I'm enjoying our conversation around like this. So in terms of these intelligent systems that are doing the context switching, like how do you see that kind of approach, and what do you see as some of like the missing breakthroughs that really need to be hit? Because when you think of a natural bilingual person, right, like myself, I speak Greek and English, and when I talk to my parents, when I talk to my siblings, we constantly switch between languages unless there's other people around, because for us it's almost like in our brain, just pick the shortest word, which word is going to like fit there but also get the idea across without having to speak too much, which I could imagine for a speech to text would just be like the wonkiest thing ever because you're just like mashing up the linguistics.
Yeah. Yeah, definitely. I mean, yeah, so we call that problem code switching within Deepgram. And code switching like is very hard because the way that problem is reflected in the way you just described, how you and your family do code switching, is that it is extremely localized to individuals and groups of people. And like every group of like the way that they code switch is like unique to them. The way they seamlessly switch between the languages and the words that they use. And they might like have new words that are like sort of a mashup of the two languages that they know, but it's only they that use those words. So it's a very localized phenomenon. And localized phenomena are hard to model. Like you need data to model them. Like you need examples of like your family code switching to really model it accurately. And so it's like sort of a needle in a haystack kind of problem in that you need to find the examples of the interesting code switching patterns and then learn how to model them. And a model like a really sound modeling approach. So I would say like as far as how do you formulate the model? I mean, you actually like sequence models work really well. Like the you know you could think of an LLM. Like how do they build LLMs that can speak different languages? You have like a multilingual tokenizer that has tokens in it from all the different languages represented, and so it could in principle form any word across any language. So you do the same thing for speech recognition, and you can train a single model on a bunch of languages, and it can sort of just naturally learn to emit predictions in English or Spanish or whatever,
Or both.
or both. Yeah. And then the question is, if you give it code switch speech, what is it going to do? And if it's never seen code switched speech before, it's likely to just be silent because it's like a new data distribution that it's never seen. And this is like what currently what the models do, when you train them only on monolingual data and then they see code switching.
They just get real awkward. They're like that guy that you start talking to in a different language. He's just, I thought I knew, but I have no clue.
It's really frustrating because like that is the most interesting thing that you're trying to model. Like that's the phenomenon, like the real phenomenon.
Give up. Don't give up. Don't give up.
Give up, venture, I guess.
So aside from just like multilingual, like context switching, that sort of thing, there's a whole nother set of detection that these models need to do. And that's around like more general, like distinguishing humans from background noise, maybe like who is the main speaker? Are there other speakers to be able to like attribute the audio to each person, right?
Yes, I would say that that is one of the big frontier problems that when we solve that one, there will be like tremendous utility to be derived from it, like a real audio intelligence, building a model that is as good at listening as a human is, listening to another person when they're in a complex environment and not only understanding what they're saying and then being able to sort of like filter out um, the noise intelligently. And then care like understanding not only what that person is saying, but what's the state that they're in, you know? Are they in their baseline or are they a little upset? Are they a little sad?
Emotional context, huge, right? Because
No context.
there is no emotional context. And now we see with like TTS, they're able to accept emotional cues so they can respond with what seems like an emotional response or mimicking response. But if you don't have that data coming in, those things aren't going to match, right? Like if I'm really upset and you're being sarcastic with me, which happens in the real world, right? Like those are real examples. People just kind of egging into something or leaning into something that's upsetting someone just to kind of like troll them. And
Mhm.
I feel like that kind of exists more on the internet than proper behavior, right? Like people look to troll on the internet. Uh, but that's a huge issue because if someone's upset, you don't want the model trolling them. You want them consoling them.
Yeah, totally agree. You have to be, the model has to be capable of really characterizing their counterparty's emotional state, having some reasonably deep understanding of it, and then being able to respond if we're talking about like a speech to speech model, being able to respond appropriately, conditioned on what the model is detecting. And the way that people have attempted to solve building this audio intelligence model so far is that they're taking LLMs as a starting point because LLMs are smart. LLMs know all kinds of stuff, and they're like, no, they really understand the content of what the person is saying, and then they're trying to like graft onto that some kind of acoustic representation or acoustic encoder. Like very frequently, people take Whisper as an encoder, and then they do some like fine tuning, some post training on that to graft Whisper on or some other audio encoder, and you get a model that does not really understand audio. And there's some interesting work about like examining the representations that these models produce internally. So you start to get the sense that like this real audio intelligence model really needs to be built sort of from the ground up and trained on some task or some collection of tasks that includes both audio and text. And discovering what those tasks are, I would say, is like then the big challenge.
Yeah, because from they only have like so much data to go off of, right? And traditionally, it's humans, organics, whatever you want to call it. Like when you're talking to someone, usually it's not over the phone so much, so you can see their face. You have other cues that can play into your decision making. Model doesn't get that. It just gets what it gets, right?
Yeah. I mean, that raises a really interesting idea, which is like maybe the way that the audio intelligence model will be trained, it'll be like it'll be bootstrapped from a video intelligence model. Like maybe that's one of the fundamental signals that you'll be able to sort of like extract knowledge from as a starting point.
It,
Yeah.
like get this multimodal one that kind of can take the two things, create the right tunings between them, and then distill out from there. It's an interesting
Yep.
idea. Um,
It's possible.
yeah, LLMs and AI have proven damn near anything's possible. Like things that people 5, 6 years ago told you, no, there's no way you could do that. It'd take too much effort. An LLM can do in like an afternoon, right? And it's insane. Beyond just like emotional context and like these really complex things, there's also like fundamental issues like in conversational dynamics that just haven't been solved, right? Like, how do you really understand when someone's stops speaking. Like that end of turn detection is so critical, but also like the start of turn, right? Like the start of speech. Is it an interjection or is it an affirmation? And like, how are you guys thinking about these sort of dynamics in the conversation?
Yeah, we're thinking a lot about them. So I would say that there are a number of models, a growing number of models that are now shipping with end of turn detection. And so people are currently trying to solve the problem of like understanding when a person has actually finished. And then they're able to then apply a heuristic that says, if I think that this person has stopped finish, now probably a good time to start speaking. And so then it's like, okay, we allow our voice agent to respond like as quickly as it possibly can after we think the person has stopped. But that ultimately will lead to conversational experiences that feel weird. They're not going to feel natural because humans are probably doing some like end of turn detection when they're like listening to someone, but they don't always wait until that person is done. They interject, right? And so there's this other signal that you mentioned, which is like, should I start now or not? And that signal is I think, much harder to model because it's like, it's subjective. It's like, is this the right time or not? And that I would say is like not really characterized yet.
I feel like people don't really get that one right. Like you said, people don't wait, they just interject. So like people in their own brains are like, idea, I have to share, and just like jump in and butt in like I did just now.
Exactly. The butting in seems like it's so situationally dependent and also dependent on the individual that it's like way more subjective and potentially harder to model. And so you can imagine like if you had a very broad corpus of data where you have humans talking to each other. One thing that you might need to do to be able to build the start of speaking model is to really characterize all of the people in that corpus as to like whether or not they're good at that. Like who are the people that we actually want to mimic and
Yes.
who are the ones that we don't want to mimic. And we can use both of those.
I feel like you said earlier though, it's situationally dependent, right? Because in some situations it's really taboo to interject, right? Versus other ones, it's almost expected. Like if you're having a heated debate, the other team is just gonna like ramble on until you interject to put your points and kind of like take derail that part of the conversation. So it's like, how does the model know when it's contextually and socially appropriate?
Totally. It's going to be like, it's more of an alignment problem getting that part right. It's like we will be able to train the start of speech signal using human conversations, and you'll get a model that exhibits all kinds of different behaviors. It'll be kind of wild. And then you just got to rein it in and get it to do what you really want, in the context. And so it is kind of analogous to like the LLM alignment stage. I think we'll have that for start of speaking.
I mean, that'll be pretty cool just to see, right? Like that'd be interesting to have that because right now, let's say you put two models, like voice to voice models, in a room together, right? And I'm sure you guys have done this. We do it all the time at Agora. It's a fun way to test your LLM, and they start talking to each other, but they have a very civilized like discourse. They go back and forth, very like almost like a show, like theater. They take the turns. They're very careful, and they don't mimic natural conversation in the sense that like if someone starts talking the other direction, they just give them their space to go.
Yeah. When you just said that, I had an image in my mind of like a puppeteer who's like doing two characters. And this puppeteer can only do one of the characters at once. And like that's kind of what a bot on bot experience feels like when you listen to it. Yeah, that's right.
And kind of going into that whole the style of speaking, right? I think that's something that we talked about the other day. Is another major challenge is like getting into adapting to how an individual speaks, right? Like how they kind of linguistically phrase things and speak in a way that's not like the normal path, right?
Yeah. Yeah, I mean that's another like emerging challenge. I think that there's like a couple of areas of deep learning that where that kind of challenge is addressed. And like these are the kinds of techniques that we're going to have to bring to bear. And the idea of personalizing a model to a particular person, that's definitely at play here. And then federated learning is another one. And so if you have a model, if you're using your phone and you have some model or some system deployed on your phone. Federated learning approaches are going to be able to update the like local weights of your model so that it works better for you. Yeah. And so we'll have to devise clever ways that like the person who's using the thing can give feedback and give a feedback signal that says, actually I meant this, and have that experience be seamless enough that they're willing to continue to use the thing.
I feel like that's being very generous to the model and the experience, because most people continue to like be like, but I meant this, and continue to mispronounce it and say it like, and then they're going to go through this like whole roundabout way of describing what they meant, but the TTS isn't going to get it, right? Like it's not a human.
No. And the success of this will all hinge on like, are you able to update the weights of the model in the moment once you get that initial feedback so that you get it right like immediately?
So like self-adapting, self-adjusting. And is that stuff that you guys are like working on, you have in production now? If you can talk about it. If not, you'd be like,
No, that is something that's like it it's like a core problem that I would say like not many people have worked on in general across the board. And it's, one of the core problems of like the next phase of, Deepgram. Yep. Models that adapt. And we've been solving that problem through training up to this point, like training highly adapted models like offline in an offline setting for customers. We had a lot of early innovations. Like if you only have an hour of data for a customer, how do you get the most accurate model possible on this hour? We ideally like to have like 10,000 hours. And so you can do all kinds of things to, in this like very low resource setting, few shot setting. It's kind of the same thing, but for the real time adaptation, some of the mechanics are going to be different. Like you won't be updating, let's say, the weights of the models. You might be able to update the activations that were produced. You'll be able to like edit them in real
take a
time.
different path down to get there. Okay.
And then you store the signature of that update that you did. And then at some later point, you can incorporate that into training. So these like activation editing approaches, they exist. There's like a handful of people looking at that are working on this.
So it's kind of like a newer thing.
Yep.
We have been going for so long, and I want to be mindful of your time because you are, a VP of research and probably have way more important things to be doing than talking to me. But I appreciate you taking all this time to like answer all my crazy questions and go down these rabbit holes with me.
Yeah, totally. I had a great time chatting with you.
We'll definitely have to do this again, like because I have so many more questions now, and I'm sure I'll have even more questions the next time we meet. But right now, I have one more question. Like that Steve Jobs, like just one more thing.
Mhm.
If you weren't working on STT, what other like voice AI domain do you think you'd be betting on next?
Yeah. So I think the problem of modeling emotion is really interesting. And that to me is like one of the frontiers that like if I was still building models, and if I have some spare time here and there, and then and like cursor has gotten good enough that like within an hour I can spin up a model, like I would like to be working on probably emotion recognition or modeling it in an unsupervised way. And like trying to utilize some ideas about like the most of the time a human is in like a baseline state, and then every once in a while they're in an excited state. And I think that like just to say one idea that might work, if you look at text to speech models and the way that they're trained, if you take a text to speech model, like the first stage of training, text to speech models are trained in the same way that speech to text are these days, a very, very large scale training first, and then a much more refined fine tuning post training. But like if you look at the model after the first stage of training, it has seen like millions of speakers in its training, and it doesn't really represent any of them particularly well. So it gives you kind of this like averaged human expression, but it's not very emotional. It's not like doesn't exhibit a lot of extremes.
Mm-hmm.
And so like a TTS model that's pre-trained on a very large corpus of data with weak conditioning kind of represents like the baseline state. And so you could take that and you could construct like a difference operator that takes some audio of a human, and then it takes like a TTS simulation of that human,
Mm-hmm.
and then it compares an embedding of the actual audio to the synthetically generated one in some embedding space. And there will be examples where that human is animated and the TTS will not be capturing that. And so you should be able to like detect this difference.
So it'd be like the differences in kind of like the pitch and inflection and like all those other characteristics that aren't really there when you see text on a page, right?
Yep, exactly. Yeah. I mean, so like this is like literally what I would do. I guess I have described it to you.
No, it's cool. We
The
don't have to
idea.
give away all the secret sauce. I think it's a really awesome approach and concept. And who knows, maybe someone's watching to let you do this.
Yeah. So, give it a shot. See what
Yeah.
happens.
So,
It's likely to not work, like for a variety of reasons.
I mean, that's what experimentation is about, right? Is it gonna work? Is it not? It's only one way to find out.
Exactly.
Well, Andrew, I appreciate your time. I thank you so much for all these like I can't even call them tidbits. These are like knowledge bombs. Like you've kind of like created these like explosions of just like extra information in my brain that I'm so thankful to have and kind of better understanding of all this like speech to text patterns.
Great. Well, I'm glad I had a great time chatting with you. Yeah. Thanks a lot.
Well, for everyone that's following along, like, subscribe, follow along with the podcast. We'll be releasing this episode in the coming weeks and keep an eye out for when we're going live for the next one. Appreciate everyone's time and see you soon.